Hello, fellow engineers. So it's been a while since the last video, and yeah, we will be continuing our simulation case, about nitrobenzene from the first part of the introduction. And in this tutorial, basically, we will just try to simulate the case in a simplified manner so that we can get used to the interface and the overall flow in the HYSYS, Aspen HYSYS. Okay, we'll still be using the same reference here, yeah, though there will be much modification that is necessary so that the simulation can run. Okay, so we'll be trying to make the simulation from scratch, and this is a new file, and we'll be going here fast. Okay, so first of all, we need to identify what's the chemical compound that's being involved within this process, and we'll be only using the main reaction, the main reaction compounds, which is the nitrobenzene, this one, and then there is the hydrogen, and then there's also the product that we want, which is aniline, and the side product of water, because this reaction is hydrogenation that leads to a condensation of water. Okay, so we'll be having this component list. We'll be listing it first, NBZ, okay, and H2, and we have the aniline, and we have the water. Okay, now we will identify the requiring operating condition here. Nitrobenzene is heated above its room temperature of 24 degree to 100 degree. So the initial condition is 24 degree, and then the after condition is 300 degree. Okay, or it is mixed with hydrogen, and the mixing in a PFR. Okay, so we'll be using a plug flow reactor. Okay, 50 millimeter and 500 millimeter long at atmospheric temperature, at atmospheric pressure. Okay, so this is important once again. So we can say that the overall condition will be around 1 atm or 0.325 Pascal, Pascal, kilopascal. And then excess hydrogen. Okay, so this is an important thing to note, because that means the reaction here, the depleted one or the limiting reactant is the nitrobenzene, whereas the hydrogen is the excess one. So yeah, we'll be adding it in excess, and as a matter of fact, we'll be adding it to a ratio of 1 to the 3, of MBZ and the H2. Okay, now we know the several basic facts. Let's now move on to the simulation. We'll be adding first, okay, the component NBZ, nitrobenzene, nitrobz. Okay, and we'll be adding this, okay, and then the hydrogen, the hydrogen, okay, and then the aniline, okay, not the oil, the aniline, okay, and then the water. Simple. Okay, it's done. Okay, now that we have completed the component list, let's now go directly to the fluid package. So in determining the fluid package, we must be able to decide what package will we use. Okay, and this is a reference that you can use, and now I have used this for some time, and it quite helps you in determining the required package. So just directly start with the first question, and with the first block. Any polar component? Yes, because we have water. Of course, it will be polar. Any electrolyte? No, because it's only an aromatic nitro derivative, yeah, from the benzene, which is the nitrobenzene, and also the product and the derivative of nitrobenzene, which is aniline. So no electrolyte, no. Operating pressure low to medium. Yes, it is stated that the pressure is only atmospheric, so 1 atm, yeah, 1 atm. Binary iteration coefficient available. Yes, this is only about the coefficient, whether it is given or there's like enough data. And yes, there is. And this is important now because will we have the liquid-liquid equilibrium? And it will be a yes, because later on to separate the product we'll be using a distillation column, yeah? And the distillation column, it'll be all in liquid form, so we must have a equilibrium there. That's why we have two options: NRTL, non-random two liquid model, or the unique quark model. And just in this case we'll be choosing the non-random two liquid model. Okay. Okay, where is the NRTL? The regular one, yeah, not the modified. This one. Okay. Double click and leave everything as else. Okay, now that we have come up with the basic things to prepare the simulation, which is the component and the fluid package, we'll be now going to the simulation. Some of the unknown. Okay, binary coefficient. I think this is Univac LLE. Okay, we'll be just setting this first to 0. It's okay. Okay. Okay, so now we are in the main UI of the simulation, yeah. Okay. And we're just gonna be having the model palette again. Okay, come up. The first one, yeah. For this first part, I forgot to mention it earlier. We'll be only discussing it until probably around the reactor, yeah. Okay. Name BZ, yeah. And then name first. The mole fraction is 1. This is only MBZ. 1000. Okay, and then okay. Okay. The condition. The condition is 24, yeah, the initial condition, and it's only of 1 atm. Yep. Okay. 101.3 kilopascal. And for the molar flow, this is an important thing, because we will be putting it in excess, and I said that it'll be in a ratio of 1 to the 3, yeah, 1 to the third. That means we'll be having this as 1, yeah, just for a simplified simulation. Okay, we got our first material stream, which is the nitrobenzene. Now we just gonna put once more the another material stream, which is the hydrogen. Okay, which is the hydrogen. H2, same 24, 100.3. Okay, and then the molar flow will be 3, and then the composition here. Okay, double click. Okay, 0, and then 1 0 0. Okay. Okay, everything now is looking good. Okay, yep, just like this. Now that we have defined the material stream, let's put some things, yeah, that is relating to the whole simulation. So we know that from the reference we need to heat up everything to 300 degrees Celsius, but if you see in the simulation, the author put a preheating to nitrobenzene. Yeah, so there's they do not directly heat everything up to 300 degree, but there's a preheating here. Now the reason to that is because nitrobenzene heat capacity is indeed high, is quite high, and if you put it directly later after the mixer and heat everything up to 300, the duty of the heat exchanger or the heater will be very much high. So we can reduce that duty by having a preheating heater. Yeah. Okay. Still looking good. Then just rotate, rotate, rotate. Okay. Now just connect first the inlet. Okay. To NBC, and then this one is, I usually just call it example heated NBC. Energy, let's just say it will be Q1. Okay. Delta P, we assume no pressure drop. Okay. Now the delta T here is important. 24 to 300 degree, there is an increase of 276 degree. Okay, done. Okay, you rotate this first. Okay, nice. Now here it's already in the required condition. Now we'll be having a mixer. Yeah, we'll be having a mixer. The mixer. Okay. And, we just gonna rotate this first, and then connect it directly, yeah, to the both streams. Hit it MBZ and then the H2. And then the outlet, we just call it a mix feed. Mix feed. Okay. Now it's looking really messy. Okay. Still looking good. Now remember, because we mix the hydrogen at room condition 24 degree and the nitrobenzene is already preheated, that means there will be a change in temperature of the mixed feed, which is about 214 degrees Celsius. That means we can now heat it one more time, yeah, as I said, so that the duty of each heat exchanger or the heater will not be that high. Mixed feed. And because after this heating, the condition of the feed will be directly suited for the PFR for the reactor, we're just gonna set the outlet, yeah, the outlet as PFR feed. Now like that, with the energy, just say Q2. And then for the delta P, 0, and then the delta T, just warm this. Okay, okay. Now 300 and still 180. Now we will come to the fun part, which is the reactor itself. So let's put a plug flow reactor. Ooh. Okay. Oops. What's happening? Sorry. Okay. Now for the reactor, we must be able to ensure, yeah, the required field is available. For example, the dimension and then the reaction. So we will be going back to the to the reaction, yeah, to the reaction set, reaction UI interface, and we'll be adding a reaction set, yeah, and F2FP, yeah, still using the NRTL, F2FP, yeah, to set package. Okay, and then add reaction. Now you're gonna see a several type of reaction, and then from the reference I have made a literature review and have found that the most available data for this reaction is a kinetic one. For conversion, it's usually for a reaction where you want a specific converting ratio, for example, or percentage. Example in just in a batch reactor, yeah. For example, a sugar refineries or in a continuous stir tank reactor. And equilibrium is just for a forward and reverse reaction rate where both pose the significant rate. So yeah, you must be able to know the constant. And then the heterogeneous catalytic for reaction with a solid catalyst, and the kinetic, well, the basic and famous Arrhenius equation. And simple rate is just a basic law, yeah, the first order, second order. I'll be using the kinetic one. Okay. Now we will be adding the component nitrobenzene, hydrogen, aniline, and H2O. I'm sorry if it's still kind of confusing. This is, well, my very early entry video, so I hope that you guys might understand. I just want to try to share what I know. Probably like this is a very basic thing, not even an advanced amateur. This is a very entry level, and even I'm still learning it too. So we'll be going here together. Now, stoichiometric coefficient, we know that from this reaction, yeah, this given reaction, we have now the balance, yeah, the stoichiometric coefficient balance, which is 1311, 1312, sorry. And for the reactant, as they will deplete, or as they will reduce and decrease in concentration, meaning that there will be a minus sign. Yeah, don't forget it. That means minus 1. And then hydrogen minus 3. Aniline is 1 plus 1 and H2O is 2. And balance, yeah, balance is 0. Means that it is all balanced well. Now the base component is what you will define as the limiting reactant. Yeah, that's why we put the base component as the nitrobenzene, because we are adding the hydrogen in excess. And then the reaction is, of course, in vapor phase, because 300 degree, it's completely vapor. It's completely vaporized. Now for the dimension, this is from the literature review. Yeah, I will be adding this to the forward reaction. Remember, this we do not account for the reverse reaction or the reversible one. Yeah, we only see it as a one-way reaction. So the A is 1, it's 1.25 E plus 0 to 2. Okay, and then 1.1 A E, okay, 1.3057 E plus 005. Okay, and that's it. It's ready. The reaction is ready. Good. Now back to the simulation. So the inlets will be the PFR feed, and then the outlet will be the PFR outlet. Energy is AQ3, and the reaction set is from the RX1 set 1. Yep. And then for the dimension, now there is the specified dimension 0.5 meter, 0.5 0.5 meter. The diameter is 0.15 centimeter. Number of tubes 1. Okay. And then for the rest, just let it be. And then no pressure drop. And then the duty, this one, you just can set it to 0 first, yeah, the duty, because the reaction of nitrobenzene and hydrogenation of nitrobenzene is highly exothermic, so it will it will give a lot of heat, and so it will give off a lot of energy in the Q3. Yeah. uh wait, the reaction here. Yes, everything is the worksheet. Oh, because I forgot that this should be this is kind of dumb, if the temperature of the outlet exceed 1571 degree, most likely your pipe will melt to the ground. Yeah, so you must make the temperature to around 300. Yeah, 300. So there is no temperature change. Yeah, because the reaction also say it does. It doesn't change. Okay. I forgot which. Where is the? It's already correct. Whoa, 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 whoa. Worksheet. Yeah, that's why to do these. I forgot. Sorry, sorry. The duty is just leave it as blank because it'll be calculated from the program. If you decide that the PFR outlet is still 300, by this you mean that the ongoing reaction will be isothermal and they will release enormous heat. See, 55 kilowatt. Okay. You can also see the result of the reactor, yeah, reaction around 42.17%. So not that high, but the reaction um, is quite okay because we'll be introducing the recycle later on. So it's okay. Now from the outlet, you see that the temperature is still around 300. Okay, now that we have come up with the outlet, yeah, at 300 degree, the isothermal, we'll be cooling it down to 50 degree. The inlet will be the PFR outlet. This one just say Q4. The outlet is PFR cooled as a new one. The pressure drop as we're gonna assume a zero pressure drop. Okay, delta P and then delta T. It's the duty. The worksheet condition. I'm sorry, guys. Active. A consistency error. PFR cooled. I think I might have mistaken where this one is should be active. I see. Okay. And I forgot the thing. Delta T minus 250. Okay, now the temperature is set to be around 50 degrees Celsius. The pressure is still there. Yeah, it's still the same. And for the next step, we'll be introducing it and explaining it to in the second part of the simulation, yeah, which will cover a flash drum or separator. Basically, because we know that from this composition, yeah, as mass, yeah, just see it as mass fraction. You see that a lot of nitrobenzene and um, H2O is still available here. But you must notice that most of the things that you want to get rid of is the hydrogen again. Yeah, is the hydrogen. Yep, the hydrogens. That's why you're gonna use a flash tank so that the hydrogen vapor will be released, and we'll check the purity. If the purity reaches a good threshold, yeah, we can recycle it back. But if it's a lot of impurities there from the water, that means for the sake of simplicity, we just gonna be having an outlet feed. Yeah, and then the effluent there will be heading towards the distillation column. Okay, then the distillation column later will have the aniline as the main product. So thank you for today's session. I'm really sorry if there is still a lot of imperfection and also many maybe not really clear explanation, or yeah, but I do hope we can get better along. There's a long road ahead. And thank you for watching, and see you on the next chapter, which is the second part. Thank you.